The next topic is process description and control. So what is a process? A program in execution is a process. Or we can also say that an instance of a program running on a computer is a process. It can be also defined as an entity that can be assigned to and executed on a processor. Okay, so two elements of process are program code and a set of data associated with the code. While the program is executing, this process can be uniquely characterized by number of elements. So now we'll see all the elements. A simplified process control block is shown here in this figure. So as mentioned earlier, process can be uniquely characterized by a number of elements. We will see all the elements one by one. First is identifier. Unique identifier is associated with each process to distinguish it from other processes. Next is state. If the process is in execution state, okay, it is in a running state. So with the help of this, we will come to know the state of the process. Next is a priority. So here the level of priority level of each process is stored. Okay, priority with respect to other processes is stored here. Next is program counter. The address of the next instruction in the program to be executed is stored in a program counter. Then memory pointers. It includes pointers to the program code and data associated with this process and any memory blocks shared with other processes. Next, context data. This is the data which is present in the registers in the processor while the process is executing. Then I/O status information. This includes outstanding I/O requests, I/O devices assigned to this process, a list of files in use by the process, and so on. And the last one is accounting information. It may include the amount of processor time and clock time used, time limits, account numbers, and so on. The information in the above list is stored in a data structure which is called as process control block. So this process control block is not a hardware, it's a data structure and which is created and managed by operating system. The process control block contains sufficient information so that it is possible to interrupt a running process and later resume execution as if the interruption had not occurred. The process control block is the key tool that enables the operating system to support multiprocessing. Thus, we can say that process consists of program code and associated data plus a process control block. Okay, so what is the significance of process control block? If you remember, okay, I had talked about page faults. Okay, so what is a page fault? CPU is first searching in main memory for a particular page. Okay, if the match is found, then no problem, it's a hit. But if the match is not found here, then the page fault will occur and the control will go to the operating system, right? So we that time I had mentioned one term that's context switching. Okay, context switching. So what happens in context switching? The control will go to the operating system will go to secondary memory, bring that page to main memory, and then again the control will be given to the CPU. Okay, so what is happening? One process is running, okay, in between the interrupt come. This is the interrupt, okay, trap. That time I had mentioned trap. So the interrupt occurs that time, whatever the execution state is, that entire information is stored in process control block, okay, and then the control come back to the CPU, okay, the CPU can start executing that same process from that particular point. Okay, so the entire information and status of that process is stored in the process control block. Next, we will see what is the meaning of process states. Processor executes instructions from its repository in some sequence dictated by the changing values in the program counter register. So here in figure A, okay, we can see there are three processes. Okay, this is a memory layout for three processes, process A, B and C. And this is a program counter. So program counter gives you the address of the next instruction which processor wants to execute. So here I have shown the address as 8000. So at 8000 the process B will start. Okay, so it is the program counter is pointing at the address location 8000. The program counter may refer to code in different programs that are part of different processes. Listing the sequence of instructions that executes for that process is called a trace. The behavior of an individual process can be characterized by a trace. Okay, so let's assume that all three processes here are represented by programs that are fully loaded in main memory. And there is also a small dispatcher program that switches the processor from one process to another process. So for context switching. Okay. So figure B, okay, shows the trace of each of the process during the early part of the execution. So this is a trace of process A, this is trace of process B, and this is a trace of process C. The first 12 instructions, see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the first 12 instructions executed in process A and process C, okay, are shown in this figure, okay. And process B has only 4 instructions, 1, 2, 3, 4. And we assume that here the fourth instructions of process B, the fourth instruction of process B invokes an IO operation. Okay, hence process B has to wait because process wants IO operation. Okay, so it will wait for IO operation. A combined traces for processes A, B and C are shown in this figure. We assume that operating system allows a process to continue execution for a maximum of 6 instruction cycles, after which it is interrupted. This prevents any single process for monopolizing processor time. So here you can see that process A starts from 5000, okay, and it will run till 5005. So only 6 instructions, okay, so till 6 instruction cycles process A will be executed. After that it is interrupted. So how it is interrupted? By the dispatcher program. And what is the starting address of the dispatcher program? 100. Okay. Again it will run for next 6 instruction cycles. After process A, process B will start running, executing. Okay. So process B has how many instructions? Only 4. Okay. From 8000 to 8003. 8003 at 8003, okay, it invokes the IO operation. Okay, so whenever it invokes the IO operation, the dispatcher program will start running. Okay, so again the dispatcher program will run for next 6 instruction cycles. After dispatcher program, process C will start executing for the next 6 instruction cycles. After that, again the dispatcher program will be executed, and after that the control will go to the process A from 5006 to 5011, next 6 instruction cycles. After that, again after process A, again the context switching will happen. It should go to the next process, right? So again dispatcher program will run, okay, but process B is still waiting for IO operation. Okay, so process B is not ready for the execution. So the control will go to process C. So process C will start running from 12006. Okay, and it will run or it will execute for the next 6 instruction cycles. Now we'll see a two-state process model. Controlling the execution of the process is the main responsibility of an operating system. In this model, a process may be in one of the two states. Either it will be in the running state or it will be in not running state. When operating system creates a process, as mentioned earlier, it creates a process control block for the process and enters that process into the system in not running state. Process control block stores the information related to current state and location of the process in the memory. The process will be waiting for an opportunity to get executed. The currently running process will be interrupted as shown in the previous um, example. Okay, what I said is process A will be interrupted. How it interrupted and what will happen? The dispatcher program will be, we are going to run the dispatcher program, right? And then the control will go to the next process. Okay, so the current process will be interrupted and the dispatcher portion of the OS will select some other process to run. The first process moves from the running state to the non-running state, and one of the other process will move from not running to running state. So figure here shows the queuing diagram. Okay, it shows the structure of the processes which are not running and waiting for their turn to execute. There is a single queue here in which each entry is a pointer to the process control block of a particular process. A process which is interrupted is transferred to the queue of waiting processes. If the process is completed, then it is discarded. In both the cases, dispatcher takes another process from the queue to execute. Now we'll see creation and termination of processes. First we'll see process creation. When a new process is to be added, operating system builds a data structures that are used to manage the process and allocates address space in main memory to the process. So two important things you have to remember in process creation. First, builds the data structure, and second, allocate address space in main memory. Okay, now we'll see the reasons for process creation. First is new batch job. A process is created in response to the submission of a job. So, for example, addition of two numbers. Okay, will create the process. Second, interactive login environment. A process is created when a new user attempts to log on. Whenever you log on to the system, the process is created. Third, created by the operating system to provide service. The OS can create a process to perform a function on behalf of a user program without the user have to wait. For example, if the user wants to use a printer, means whenever user wants to print a document, the operating system can create a process that will manage the printing. The last reason is what? Spawned by existing process. What is the meaning of spawning? Generating. Okay. So for purpose of modularity. Now what is modularity? The concept of making multiple modules first and then linking and combining them to form a complete system. Okay, so for purpose of modularity or to exploit parallelism, a user program can dictate the creation of a number of processes. So, in short, one process may generate another process. So, one example I'll give you here. If you want to compute the average of 100 numbers and you have assigned that those 100 numbers to a single process, okay, so this is called as a uniprocessor system. So one process is handling 100 numbers to compute the average. Instead of that, if you have 5 processes, okay, and then you can divide these numbers, 20 numbers to each process, okay, and each process will just compute the average of those 20 numbers, and at the end we can combine the result. So this is called as a parallel processing. What we are doing is we are taking one task, dividing that task into subtasks and assigning it to different number of processes. Why are we doing this? Okay, the intention of doing this is to achieve a speed up. Okay, so in this case, what I'm trying to tell you is there is one parent process which can generate 5 childrens and assign the tasks to it. Okay, so when the operating system creates a process at the explicit request of an other process, the action is called as process spawning. When the process spawn the other process, then the former process is called parent process and the spawn process is called child process. The processes should communicate and cooperate with each other. Now we'll see process termination. A computer system must provide a means for a process to indicate its completion. A bad job should include a halt instruction which will generate an interrupt to alert the operating systems that a process has completed. For an interactive application, the action of the user will indicate when the process is completed. So, for example, when user logs off or turns off his terminal, okay, the process is terminated. On a personal computer, when user quit an application, maybe a Word, Microsoft Word, PowerPoint, okay, operating system gets a request to terminate the process. Another example is arithmetic error, or you can say division by zero, can also lead to the termination of a process. In some operating system, a process may be terminated by the process that created it. Means the parent can terminate a child process. Okay? Or when the parent process is itself terminated, that time the children will be killed, okay, by default. There are many other reasons also, like time limit, if the time limit is exceeded for a particular process, okay, or maybe memory, if the memory is unavailable, okay, that time also the process will be terminated. Or if process tries to access a memory location which is not allowed to access, then also the termination will be there. Or if it tries to access resources which are not allowed to access, then maybe in case of IO failures, unable to access, then also the process termination will occur. Uh, when it will attempt to execute a non-existing instruction, that time also the termination will happen. Or maybe if the process attempts to execute uh, a reserve location or a reserve resource uh, for the operating system, that time also the termination can happen.